All right, hey everyone. This is chapter two, chemistry and measurements. Um, I'm going to walk through a couple of the questions I've been getting first, kind of catch everybody up. Number one, we got Mastering Chemistry that was due last night, so February the 7th, but I'm still getting people added into the course, and we have some people that don't have money or hadn't got their materials yet. Um, I'm going to be a little uh, gracious with those assignments. Go ahead and get them turned in. Don't worry about it. It'll probably read zero initially. Just email me, let me know that you completed it, and I can go in there and adjust your grade. So you had two assignments done this past week. First was Introduction to Mastering Chemistry, and then Chapter 1, Chemistry in Our Lives. This week I'll be adding Chapter 2, Chemistry and Measurements to Mastering Chemistry. Those will be done. Those will be due by Sunday. Okay. What? Any other questions that I need to answer? Let me show you what we got going on Cougar View. So this video will be there pretty shortly. But I've also added all these other links. So we're going to go through the lecture today. If there's any particular area that you're not really grasping or didn't cover fully enough, and there won't be. This is more or less an overview, and it shows you how and where to get the information. Now I will help in any way I can. If you get stuck, you can email me, obviously. But these videos are also very helpful. So particular topics here, density, prefixes, the unit conversions, and then also a video from last semester that I thought was very helpful for some, where I just go through and work a bunch of practice problems. So you'll hear a lot of the same stuff I'm going to say today on there, but it's just because I'm trying to drive those ideas home, right? Those methods or whatever it is. I'm trying to repeat them enough that they'll kind of stick. All right. So be sure to check all this out. If you get caught on anything, check these videos. Email me if you're still stuck. Um, but with that being said, let's get into it. I know some of y'all need to get this done so you can work on last week's lab, right? I let my lab put off this week so they can have this lecture. Let's get into it. And I'll try to go kind of quick because you got so many other materials that you can use. So I'll just try to mention the most important things, and then if there's anything you need to focus on, you can use those other resources to do that. All right. So these are the PowerPoints. I've provided them. You got to go in there and check them out. All of these vocab words will be used um, either in a question or in some type of context for this course. So it's important that you kind of understand if I say any of these, you need to kind of recognize what it is, right? Oh, one more thing I do want to mention before I get too deep into it. I've also added a review section with a midterm study guide. Okay, so this will tell you exactly what you need to be getting from each chapter. So for chapter one, it was the scientific method, be able to interpret graphs, and scientific notation. Okay, how to write numbers in scientific notation. For chapter two, it'll be the units of measurement, significant figures, conversion factors, prefixes, and density. All right. So, and then when you go through and do your master in chemistry, you'll notice which ones you're having problems with or which ones are more difficult than others. And that's probably why I got these extra videos under chapter two, because some of this can get a little tough, right? The density can be somewhat confusing. And that's why I'm gonna go through it. You'll hear a bunch of the same stuff over and over. Like I said, I'm just trying to drive it home. Okay, so chapter two. You'll have to apologize. So I'm also caretaking this week for my grandmother. That's why this video is late. I'm gonna have some issues doing certain things, but uh, either way, I'll be here all week. I'm taking off this week, so if you have any emails or questions, let me know, and I can post some more videos. I plan on posting a video about like frequently asked questions because I keep getting a lot of the same stuff. But just know that if I'm a little bit behind, I apologize. Um, I'm trying to get caught up. Just bear with me, okay? So for chemistry and measurements, all right. So a measurement is these kind of bigger concept ideas, how we define different things in our life. So the volume of something is how much space something occupies. So like a 20-ounce bottle of Coke, or a 12-ounce cup of coffee, 2-liter bottle of water. So the measurement is the larger concept idea. The unit is what we measure that idea by, right? So a volume can be measured in ounces, liters, cubic centimeters, right? The cc, you've heard that in medical terms. All of these are different ways to express volumes. Now the difference is which system they are. um, English system uses what do we use for volume? Ounces, I guess. Ounces for volume. And we use for length, we use inches, feet, yards. For mass, another way to say mass is weight. So that could be your pounds in the English system. Temperature, we use Fahrenheit. 100 degrees outside is really hot, Fahrenheit. But 28 is getting hot in Celsius. So they're different units for the same measurement of temperature, right? So make sure you keep those straight. A measurement is the big concept idea, and then the metric or the unit is the thing that is measured by. We measure time is another one. Time is measured by seconds, hours, minutes, days, years, all different types of units that we can use to measure the same amount of time, right? 7 days is 1 week. Those are the same amount of time, but it's two different units that I've expressed that in. So time is the measurement, the unit is seconds, or the unit is weeks, okay? So that's the measurement. Go back to, I think the PowerPoints do a better job with this chapter, but I will come back to the text here again. Okay, so we'll just kind of briefly mention each of the different measurements that we're going to look at. Length for the metric and SI system. Actually, let me go back to text real quick to mention that. The SI system on the far right is what we call the International System of Units. And what that means is just, as I said, we have the English system that we use here. Then you have the metric system that's used in Europe and other places. The SI system was developed for everyone to use together. So when I call someone in France and I say, I have this mass of so and so kilograms, I know that he uses that unit as well, because we've both been taught that when we publish papers or whatever, we need to use this same unit because everybody is on the same page. And that makes reading information or transferring data or all that stuff, communication is just easier if we're using the same unit. If I say I weigh 200 pounds to some guy in Europe, he'll be like, I don't know how much that is, because he uses kilograms. Okay, but the System International says we all use this, so that's what you need to use as well if you're going to be in that community. So this international system is a way for all the scientists around the world to have be on the same page in terms of units. Okay, mostly it's the same as the metric system, but there are some variances. Okay, all right. Now for the length of an object, the SI system is the meter, and a smaller unit of that would be the centimeter. You'll notice here that 1 meter is equal to 100 centimeters. This is called an equality. Okay, an equality is when I set one thing equal to another. Okay, notice that these are different units. Now I can use these equalities to do my math work, to convert from inches to centimeters, or from meters to inches, or from centimeters to meters, so on. Okay, so those are called equalities, and I'll show you a little later how to set that up. Um, Debating on that because I still don't have my iPad. I got a new one on the way. It's something with my iOS. I got to get an update for this program that I'm running, but my iPad's so old that I can't update it. So I'm working on that. I'll have it figured out hopefully soon. But that's also why I included this other video with the practice problems. I do a lot of the equality stuff in there, and I go over exactly why I do what I do. So for the math in this chapter, use that video. Okay, just like I said, with everything I got going on here at the house, that'll be easier for me this week. Okay. Also got a big glare. It's just that time of day. I usually film in the morning, but if you'll notice, I got a huge glare coming in on my little board there, so I don't want to use that either. I apologize. Like I said, I think you're going to have plenty of the information that you're looking for. If it's the math and the qualities, when we get to that point, check out the other video. I do a lot of that on there. All right, so the volume is the amount of space that something takes up. We think about it like in terms of liters, like a 2 liter bottle or a gallon of milk. Those are different units for measuring the volume of something. Now, it's also important to remember that a volume can be like a square, a cube, right? Let me come to me. Say this little charger here. I got this little cubic charger, square kind of charger. And I say this is a centimeter high, it's 5 centimeters long, and 2 centimeters across. Okay, so to get the volume of this object, the volume of a rectangle, right, is the length times the width times the height. So 4 times 1 would be 4, 4 times 2 would be 8. This is 8 cubic centimeters. Okay, 8 cubic centimeters, roughly. I'm just guessing, but the point is that a cubic centimeter is also a way to express volume. Okay, if I look at my text, you'll see on the chart there that the SI system for volume is actually the cubic meter. So that's a big volume, right? Meter wide, meter thick, and then meter deep. So it's important to remember that a length in 3 dimensions becomes a volume. In 2 dimensions, it's an area, right? Length times width, that's just the area. And you know, like when you've done your math back in the past, if you want to find the area of a square, you multiply one side by the other. Well, for volume, it's 3 dimensions. The length times the width times the height makes a volume. And that is actually the same thing that we're doing here, except for you have to use graduated cylinders or beakers or something to measure volumes of liquid, something that I can contain, right? That's why we use these containers to measure volume in that way. But it's the same idea. It's the length times the width times the height. And this, for the graduated cylinders that you see here in your text, those have all been calculated and standardized so that I know exactly when I go up this much, it's 1 milliliter or 10 milliliters, right? All right. They got an image of a balloon here. That's another good way to kind of think about it. I've included a video, and it tells a cool story about Archimedes and kind of the initial discovery, quote unquote, of density or volume, displacement. All right, he got into a bathtub and the water level rose, and he said, "Well, I bet that's the same amount that my body takes up. That's the same space that my body took up, was how much the water level rose." And true enough, he was right. So now mass, make sure y'all see what I'm saying. Mass is another way of just saying weight, right? In America, we say I weigh 200 pounds or whatever. If I said that to somebody in Europe, he wouldn't know what I was talking about. They measure in kilograms. So the SI system is also kilogram. So it's important to remember that you will not hear pound much at all in science, although I will test you on it just to make sure you can do this conversion, right? 1 kilogram equals 2.2 pounds. 2.20 pounds. All right, temperature is measured in Celsius and Kelvin. Kelvin is just 273 plus Celsius. All right, so they are pretty much on the same scale. One's just lower than the other. Kelvin is absolute zero, and then if I add 273, I get to Celsius zero, which is the freezing point of water. But we'll do more practice on that. Time is in seconds. We talked about time, right? It's this big concept idea that things move forward, but how do we measure it? We have to measure it in seconds, times, minutes, days, hours, all these different things that we can measure it. The SI unit for time is the second, right? Because it needs to be smaller because things happen really fast. In fact, we have to get into microseconds and nanoseconds for some of these reactions that happen in chemistry. So time is kind of a universe. We all understand time the same way, essentially, right? So second, you're not going to see English and metric units for time. I'm pretty sure they're all in seconds, minutes, hours, days. Okay. Study check. I'll let y'all do that. So I believe if you open up these PowerPoints and click on them, it'll actually give you the right answer. It describes length, mass, or volume. Well, we'll do this together. Bag of onions has a mass of 2.6 grams, so that kind of gave it away. But you would look for the unit. What I would do is look for the unit. So kilograms, and then I go look at my chart. Kilograms is a mass, but you should know this, right? Because the pounds is kilogram. You'll get there. It's going to come easy to you. 1.7 meters, so that's a length. 0.5 grams, that's a mass. 1.5 liters, that's a volume. Okay, so you just kind of recognize these things as those measurements. So let's talk about measured numbers and significant figures real quick. A measured number is just, we use like the graduated cylinder or a ruler or something to make a measurement, to take a measurement in certain units. So a ruler can come in inches or centimeters or whatever, a meter stick, a yard stick. For this course, you're pretty much always going to use the SI units, okay, or the metric units. Metric SI are pretty much always the same. If not the same, they're related, right? Celsius is on the same scale as Kelvin, so even though they're two different units, I can use them both. Always use centimeters in this class, but one thing I want y'all to do is to be able to estimate numbers, okay? For example, on this ruler, you'll see that the ruler falls directly in between 4 and 5 centimeters. Now, I don't want to just say 4 centimeters because that wouldn't be as correct as I could be. I don't want to say 5 centimeters because that wouldn't be correct as I could be. What I would do is estimate where in between the 4 and the 5 is. And usually I just go for 0.5. You don't want to get too cute and say, well, 0.26, you know. Just go for the middle. If it's in between, just say it's dead in between. And I would call this 4.5 centimeters. Now that 0.5 on the end there is what we call an estimated digit. And that's something that the scientists will add to measurements to give more significant figures. All right, so now what is a significant figure? A significant figure is everything. Let me switch to my paint. Just a second, let me find it. Where's it at? Paint, erase. Here we go. Okay, so a significant figure is, let me see if I can just type on here. All numbers that between 1 and 10 that come after a decimal. Hold on, let me just write one out here. 2000. I'm gonna do 2200, 2220, 2222. Okay, so a significant figure is everything between 1 and 10 that comes in front of a zero or behind a decimal. All right, so for this first one, this one has one significant figure. The 2 is the only significant figure in this. All the zeros after it, we assume they're just rounding, right? They rounded to 2000 from 1996 or something like that. So the 2 is the only significant figure. In the 2200, there are two significant figures. I guess it's confusing when I got all these 2's in there. There are two significant figures in 2200. Equals 2, and I usually write sig figs like SF, okay? So this has 1 sig fig, and this one has 3. So you see the trend there. All the whole numbers before the 0. Now there is an exception when you start adding decimals though. Equals 4 sig figs. All right. So for example, if I do 2.000, all zeros after the decimal are significant. Okay, so these are just little rules, and I think one of the videos I have actually goes through these a lot more defined. All zeros after the decimal are significant. All zeros in between whole numbers are significant. So if it was 2020, I would have 3 significant figures, okay? Because the 0 in between the two 2's is a significant figure, okay? So just when the last zeros before the decimal are, we assume they're rounded. If there's no decimal, we assume it's rounded. If there is a decimal, those become significant, all right? So what did that mean? Say 20, I'll just say 20 equals 1 sig fig, while 20.0 equals 3 sig figs. Okay, so you see how that decimal adds significance to those zeros. All right, so that's how we use sig figs. It's important to always keep as many sig figs as possible, and that's why we do the estimations for the estimated numbers. If I add the 0.5, I made this, instead of just having 4 centimeters or 5 centimeters, 4.5 makes 2 sig figs, and it becomes more precise. All right, so that's why we use sig figs, how we use them. There are math. When you do math problems, it's important to keep up with the lowest number of significant figures, because you are always going to use that number of significant figures. I do more in my other videos. Let me come back to this. Let me move this over here. Oh, sorry. Let me cut that out. All right, so for example, let's do a math problem. Let's do 2.1, and then I'll do times 30. Okay, so one number has, one number, that little star is a times. One number has 1 sig fig, the other one has 2 sig figs. So I'm gonna write underneath it 2 sig figs there, and then the 30 has 1 sig fig. Okay, so 1 is the lowest number of sig figs. When I express my answer, I can only use one significant figure. So 30 times 2.1 will be 6.3, 63. 63, but I can only use one significant figure. So if I write 63, that's 2 sig figs. I have to round it off to 0. Okay? So that's how you use it in multiplication. In addition, it's a little different. So let me write these above each other so you can see it. Let's say 5180 plus 200. Let me try to get these lined up. Okay, so when I do addition, I have to round off at the last significant figure to the left. What does that mean? So let me add this up just plain and simple real quick. Plus, let me space that out there. And then equals, I got a little line here. Equals 5380. Alright, so now when I say the last significant number on the left, I come to the left on the 518. So the 8 is the last significant number that I can use. That's in the 10 spot. Remember we talked about that last week. On the 200, the 2 is the last significant number. It's in the 100 spot. So the hundreds is the last one that I can estimate on my final value. So instead of 5380, I would say 5400. The 4 is in the 100 spot. That was my my most significant number to the left, okay, for the 200. And whichever one is like the furthest away, that's the one you have to use. Furthest to the left, that's the one you have to use. Okay, I did some more examples on the other ones, and then I've provided the videos, but I do want to mention that and why it's important for us. Let me get y'all back to here. Okay. And so this the PowerPoints also go through each one of these. Okay, so for when you download this PowerPoint and open it up in your Microsoft Office or whatever, you can click on these and it will go through and kind of tell you. So the first one will be 4.5 centimeters. You have to include your estimated digit. The second one would be about 4.55 centimeters, I'd say. And then the third one will be 3.0 centimeters. Okay, I add a 0. If it's sitting right on the line, I add 0.0. Well, so here's my little rules. All non-zero digits and zeros between digits. Non-zeros that act as placeholders before digits and zeros at the end of a decimal number. Okay, so this is a little clearer. I hope that the practice doing the problems I kind of showed you some of the different things that can happen when you're doing it. See, and this is like a whole table. I think you ought to get it from what I was saying. But just so you can go through and test yourself. Zeros in between whole numbers are significant. 0 in between whole number is significant. 0 in front of a decimal is significant. 0 after a decimal is significant. In scientific notation, the tens and stuff for the notation is not significant. You just use whatever numbers on the left over here. And then it shows you also non-significant numbers. So I shouldn't have said all zeros behind the decimal, because you will see stuff like this where 0.000, all zeros in front of whole numbers are also not significant. Okay, if there's no other numbers in front of it, right? In between two whole numbers, in between two counting numbers, significant. In front of a whole number is not significant. So like 0.075, the two zeros in front of the 0.75, 0.075, the two zeros are not significant. All right. And I included a video on scientific notation. I think we actually covered that a little last week, how to count decimal places or whatever. Okay. Exact numbers, we don't talk about that too much really. How to use significant numbers in calculations, so that's what I was talking about with the addition and the multiplication. Subtraction is the same as addition. Division is the same as multiplication, is in terms of the rules, right? Uh, Lowest number of significant digits for multiplication and division, and then the last place of significance on the left for all of the values that you're adding or subtracting together. Okay. Let's skip on down because, like I said, I got the good videos on all of that. Study practice, that's fine. Hundreds, thousandths, we know how to do all that. Let's get down here to prefixes and equalities. Okay, so for this, I'm going to go back to the text. And I want to go back to the length right here. All right, so you see how it says 1 meter is equal to 39.4. That is called an equality. And we use equalities in chemistry to be able to convert from one unit to another, right? If I tell somebody that I'm 200 pounds and they say, I don't know what you're talking about, and I say, well, let me convert that into kilograms, right? So, 200 pounds in kilograms could be expressed like this. I keep doing that. Stop doing that. Where's my paint? Did it go away? All right. So, for example, I'm just going to write with my little pad here. A 1 kilogram, oh, that's ugly, equals 2.20 pounds. There's a little dot right here. 2.20 pounds. Okay, this is what we call an equivalent. Okay, or equality. Excuse me. Make sure y'all still there. I lost it. An equality is something that we can use to do equations. So one way I might write this, since these are equal to each other, I can write them over the top of each other in a decimal, and that ends up being 1. Okay? Right? Because anything over itself is 1. Since 1 kilogram is equal to 220, it's essentially saying this is 1. Now, this is useful because if I were trying to solve a problem, I could use this equality to help me do that. So say I weigh 200 pounds, okay? I don't, but just let's say that. I wish I did. 200, and I need to figure out how many kilograms that equals, okay? So, what I want to do is use this equality that I've just made on the left. 1 kilogram is 2.20 pounds. Okay, so if I multiply these times each other, right, and I can put this over 1, because I can put anything over 1 is itself. 200 pounds over 1 is still just 200 pounds. So just to make it seamless and look good, I'm going to put 200 pounds over 1. And now I can multiply this problem out, right? My pounds will cancel because one's on the bottom, one's on the top. My kilogram stays up top, so it'll come over to the right. And then I can just divide 200 divided by 2.2. 200 divided by 2.2 equals 90 kilograms. So this is 90.9 kilograms. kg. Now go back here and figure out significant figures. I have 2 on that conversion. I have 1 there, so I can only have 1 significant figure in my final problem. I'll make this 90 then. 90 kilograms. Okay. Uh, I do a lot more on this other video that I've included, the density practice problems and everything. I go through equalities and show you how I stack them up or whatever. Uh, but that's how we use them. Okay, we create an equality, we make something equal to something else, and then I can cross multiply, cancel like units to get to whatever I'm trying to solve for. All right. Now, that is for equalities. Well, actually, before I get into that, let me show you one more equality. So you also have you can use equalities that can go between different units, right? Oops, sorry, wrong one. But I can also use equalities to go between prefixes. Okay, so remember we said that 1 meter is equal to 100 centimeters. Oh gosh, that's ugly. Back. 100. Oh, it's even worse. 100, real slow like, centimeters. Okay, so if I were writing this in equality, I would just say 1 meter over 100 centimeters, like this. But you'll notice that these two are both essentially the same units or the same type of measurements, right? 1 meter is equal to 100 centimeters. If I want to know how many centimeters are in a meter without having this handy, I can go to my prefix chart. And that's what these prefixes are all about. Let me see where the chart is, right here. Okay, so a centi, which is what we've been working on, make sure y'all can see what I see. Centi is right here. The letter is a lowercase c. The scientific notation for it is 10 to the negative 2. So let me show you what that means on this right here. Okay, if I multiply, oh, where is it at? 1 meter times 10 to the positive 2, I will get 100. Okay, so what it's saying is that a centimeter, 1 centimeter, is a meter times 10 to the negative 2. Okay, so let me just clear this off and repeat that one more time. The chart that you see here, when it has a scientific notation, if I'm going from a smaller unit to a bigger unit, so let me do it like this. 1 meter is this long, 1 centimeter is this long. Okay, make sure y'all can see it. All right, if I go from a bigger value to a smaller value, I have to go bigger in size. What does that mean? So this is 1 meter. This same line would be 100. Let me erase this. 100. Why is that so? Sorry, something ain't right, man. Ah, stop it. Come on. One meter is also another way of saying 100 centimeters. Okay? So notice that if I go down in size, right, 1 centimeter this now I know I had this over here. 1 centimeter is smaller than a meter, right? So if I go down in size, I have to go up in number, right? So 100 centimeters is 1 meter, but a centimeter is much smaller than a meter. And it also works if you go the opposite way. So a meter is much larger than a centimeter. So if I have the same length in centimeters and meters, the number for centimeters will be much higher. All right, so let me just do a couple like real quick conversions. So 7.8 meters, right? The meter is a bigger unit. So if I go to centimeters, the number has to get bigger. 780, right? By power 10 to the power 2. That's why I went up 2 spots. Let's go the other way. 680 centimeters. Okay, the centimeter is a smaller unit, so if I go to meters, I have to get a smaller number. If I go to a bigger unit in size, I have to get smaller in number. So this times 10 to the negative 2 equals 256.80 meters. Okay, so that's how you use that unit conversions. Whatever the prefix is, you see what the scientific notation for that is. So the numerical value or the scientific notation, those are both the same thing. And then you can use that to go up or down in size, depending on which way you're going. If you're going up in size, you're going down in number. If I'm going down in size, I'm going up in number. So just flip either 10 to the positive 2 or 10 to the negative 2. You can go either way depending on which way you need the answer to be. Okay? And like I said, go check out the practice videos. I do a lot of these problems and work through equalities step by step on my iPad. It's much better, much more seamless than this little paint program. And it's hanging me up and it's getting me off of where I want to be. So good. Check out that video if you want to do some more practice on those type of problems and see some more explanation on that. Alright, so length, I feel pretty good about that. Volume, we typically measure in like a beaker or something, but it's important to remember that a box can have a volume too. The cubic centimeter is the exact same, is equal in fact to the milliliter. The cubic centimeter is equal to 1 milliliter. So the cubic centimeter is another way of expressing volume. Mass, we use grams. You'll see mostly smaller conversions, right? Like microgram and centigram. We rarely go higher into like kilograms and stuff like that, but I will test you on that just to make sure that you got it down. And now another important note to make about all these prefixes is they're interchangeable, okay? So I can use kilogram, decigram, centigram, milligram. I can also use it for volume, megaliter, kiloliter, deciliter, milliliter, liter. I can use it for, what else we got? Length, mass, length, kilometer, millimeter. What's my other unit? Not really temperature or time, but definitely volume, length, and mass. Okay? You won't see it much in time because as we get 60 seconds becomes an hour. It's not really the same type of prefixes or conversions. Temperature is the same way. You wouldn't say kilocelsius or anything. It's just 1,000 degrees Celsius. Oh, excuse me. All right, so where was I? Mass, the conversion factors and inequalities, that's what I was showing you there, and that's what I go through in detail on my other video that I provided. So go check that out. I worked through several problems. It's like another 40 minutes of work on there. So I don't want to waste too much time on this. All right. Conversion factors. No, skipping all that because I do all that. I did want to mention density though. Yeah, and like I said, don't worry about it. I worked through a lot of this on my video, but if you get hung up on something and you want me to do some more, just send me email and I can do a personal video or work a problem that you're specifically having and send that to you, a direct link to you. Okay, so the last thing I want to mention for today is density. Now, density is when we use two of these measurements we were talking about, mass and volume, to give an object a property. Okay, one of the like age-old little jokes concerning density is an old guy will ask, a younger kid, "Hey, what weighs? I'll give you $1 if you can tell me which weighs more, a ton of bricks or a ton of feathers?" And the little kid says, a ton of bricks, obviously. And the guy's like, "Nope, a ton is the weight, right? So you have a ton of feathers and a ton of bricks. They weigh the same. The ton is the weight. What's getting in your head and what's confusing the kid is that a brick is much more dense than the feather is, right? It would take like a car full of bricks to hit a ton as opposed to, a whole auditorium or a stadium full of feathers to reach one time worth of feathers. And so that density is this measurement that we've created to be able to express that. How much mass can I fit into a space? And we call that mass per volume or density. All right? And so that's what density is. It is mass per volume. When I say per, I like to think of this little denominator there because that's what it means. Mass over volume is mass per volume. All right? And so the density of a brick would be much higher than the density of a feather, right? And so that's where the kids get messed up in that joke or in that trick question, right? He's thinking of the brick as being so heavy when in fact, the guy told him that you have the same weight of both objects, but one is much more dense and so will require a lot less to reach a ton than the feathers, okay? So, um, and it's always expressed in this way, mass over volume, and we call it grams per milliliter or grams per cubic centimeter. Gas, we express in grams per liter because a gas it fills up much more space, and so we have to be able to measure that space easily. Um, Water, interesting to note, is exactly 1.00, and that's because 1 gram of water is equal to 1 milliliter. We set up all of these units and measurements based on water. We said, well, what we did was we measured 1 centimeter, 1 cubic centimeter of water, took the weight of that, and then set that equal to the gram. Okay, so the water always, always, always is 1 gram per milliliter and is like the basis for all other measurements. All right. Calculating volume by displacement. So this is, when you go watch that video, you'll see the guy gets in the bathtub, lifts up the water, and however much volume is under the water is how much the water lifted. And that way I can tell exactly what volume was in the water. So what you'll do, this is what you'll do in lab as well, is you'll have a graduated cylinder, you'll drop an object in, the water level will raise. So you'll take an initial volume and a final volume, and whatever the water level raises, that was the volume displaced by the object. In terms, that is the volume of the object. Okay? But Jamie will go through this in lab. You'll do this several different times. I'm not going to harp on it too much. All right, and then, like I said, I do the density problems. Specific gravity is just comparing the density of one substance to the density of water. Like I said, water is the basis for all of these units. Um, so we like to compare it in that sense with water. The density of water, as I said, is 1.00 milligrams per milliliter. So when you compare something to it, you just put that over 1. If the density is higher than water, then it'll be greater than 1. If it's lower than water, it will be less than 1. And what specific gravity essentially tells you is just whether or not something will float in water. All right. If it's lower than water, it'll float. Denser objects will sink to the bottom, like a rock. A rock is much denser than water is, so it just falls to the bottom. And that's kind of what density tells you, is how things float or how things will react with each other. Typically, things with the same density will be in the same water level, right? That's why oil floats on top of water, because it's less dense and all the oil will sit together on top of the water, creating two different levels. Okay, so that's it. Like I said, check out those videos. I do a lot on density. So density, we use this thing called a density triangle, and it helps you to set up the calculations. Be sure to check out that video. It saves lives when it comes to test time. Okay, it's very easy to use. You just set up a little triangle. You figure out what numbers the problem gave you. You plug those in, you do the math, and you figure out the answer. So go through there and check those out. I will be posting the lab later on this afternoon. I have to upload some more videos, but y'all let me know if y'all have any questions, and I will see y'all next week. Okay?